So first, thanks for the invitation. It's nice to be here. And I see I don't know many of you, so I hope we'll have the occasion to meet more in these days. Today, I'd like to present some results about non-uniqueness in the context of Navier-Stokes. So let me recall Navier-Stokes. As introduced by Elena in the first 2 days of the conference. So we have an incompressible fluid. And the equation that is solved by the fluid is a transport part, which doesn't in principle keep the incompressibility condition, which is then corrected for by a pressure. And it has a diffusion term, Laplacian of U. And for the scopes of the talk, in some results, we will have a force, a body force called body force in the right-hand side. OK. So some comments, just this term, thanks to incompressibility, can be rewritten as divergence of U tensor U. Then what else? OK, we will study typically the Cauchy problem for this, because we will be talking quite a bit of non-uniqueness. And this means that I want to fix an initial datum, U at time 0 equal to a certain U0. OK. Then, without force, to have non-uniqueness, this U0 will be a bit rough, cannot be too smooth, as you have seen. OK. Then, what else we will need? We will need the energy. This is perhaps the only useful quantity we will, which is conserved by the equation and as a sign. So how do we write the energy? We take this equation, we multiply it by U, and then we integrate. So let's do the first step. So this is the so-called local energy equality. We multiply by U, and you get dtu squared. These two terms, when you multiply it by U, I'm sure you have done this computation before, so I don't explain it too much. But comes like that. And then the Laplacian has a term which is in divergence form, and a term which has a sign, du squared. OK. So then I can take this and space-time integrate in 0t and R3. I suppose everything is smooth and nice decay at plus infinity. And what do I get? OK, here I forgot the body force. The body force is a plus Fu. If I integrate in R3, I get the following formula, that U squared at time t integrated on R3. This gives me this term, and a term that I will put in the right side, which is U0 squared. And maybe there is a factor 2 that I should add somewhere. So this is when I integrate in space-time this object. When I integrate this, and also here there is a divergence of gradient. When I integrate a divergence on R3, it vanishes. Then I have du squared, which comes here and I need to integrate it in space-time. And then I have the integral of fu. Again, integrated in space-time. R3. OK. OK, this formula is called the energy equality. And it says that, in particular, I can control this quantity just from the initial datum. OK? Or in reality, OK, when there is a force, there is this extra term fu. But this is harmless because under very reasonable assumptions on f, like L1, L2, that we will put from now on, you can apply Holder on this and reabsorb the part in U here up to losing a small part of this number. OK? So what I'm claiming is if I control the L2 norm of the initial datum, then I control this quantity on a solution that conserves the energy. So in particular, I control a derivative in space, integrated, so in L2 space-time, and the so-called L infinity in time L2 norm. OK? Maybe, I mean, if you want to do this claim easy is suppose f is 0, then I'm saying something that, is it clear? Are there questions? OK. OK, then what else? The role of the pressure. OK, the role of the pressure is to keep incompressibility. So it has to compensate for the divergence that is created by this term along the equation. So if I take, so to study this, I take the divergence of the equation, and I find that minus Laplacian of P is equal to the divergence of this term. So divergence of divergence U tensor. OK, when f is 0, let's say. OK, so the pressure solves this elliptic equation in terms of the velocity. And so in all our arguments, the role of the pressure will be the same as the one of U mod U squared, let's say, via Calderon-Zygmund, OK, in all, say, LP spaces or Sobolev spaces. The pressure will not play a fundamental role in what I will say. I mean, it must be there, because otherwise the equation doesn't make sense. But we will easily take care of it. And maybe at a first sight, one can also think to ignore it and pretend it's not there in the equations. When f is not 0, the observation is that I can suppose without loss of generality that it's divergence free. Divergence of f is equal to 0. Why? Because if I take a vector field f, I have the so-called Helmholtz decomposition. I can write it as a sum of a gradient plus a divergence-free part. OK, this is true for any L2 vector field. And what is the gradient part? So there is a divergence-free part, which is f minus. You can write it explicitly. So you have a vector field which has a divergence which is non-zero, because otherwise I have nothing to do. I take the divergence, and then I compute this operator. This operator kills the divergence, because if you compute the divergence of this part, so this part I will call the projector of f onto divergence-free vector fields is divergence-free. And then I have this part, which is a gradient. So this part is a gradient of something, so can be hidden in the pressure. So up to changing the pressure goes in pressure. Okay. So my force, I can assume it divergence free. Okay. Then, which kind of solutions we want to consider for this Cauchy problem? Well, in principle, like classical solutions. But the problem with classical solutions, even when the force is 0, we don't know how long they exist. Okay, even for smooth initial data. Then we can go to the opposite side and say, okay, what is the minimum regularity I need to give a meaning to the equation? Well, since everything, so like here this operator is a divergence of something, when I interpret it in distributional sense, I need only this term to be locally L1, no? In order to give a meaning to the equation, because all derivatives would go on the text function. So I could define a distributional solution, and they require not only U to be L2 lock in space-time. Let me write in Tx. In between, there is an important class of solutions, which are Leray solutions, which essentially are distributional solutions with non-increasing energy. So plus this, which I will call this, say, with less or equal. Or you can do a variant of it. Here I did it between 0 and time t. You could do it between 2 times s and t, and so you have really, like, when there is no, a decreasing property of the energy. But yeah, it will not change. Both notions are fine. And the important property of Leray solutions, which is this breakthrough of Leray in 34, which was also one of the papers which popularized the Sobolev spaces and used in PDs of Sobolev spaces. So Leray Act 34 is that Leray solutions exist. So for every U0 in L2 initial datum divergence free, Leray solutions exists globally, so for every time. From U0. And sorry, maybe if I state like that, let me state the version with the force. So then I have for every U0 in L2 and for every F, which is in a reasonable space. No, I mean, in order for this theory to work, this energy must be coercive. So I need this term to be reabsorbed partly, so the U in this term to be reabsorbed either in the first one or in the second one. If I need to reabsorb in the first one, by duality, the force, I need to apply Holder, and by duality, the force has to be in L1, L2, L1 in time, L2 in X. If I want to reabsorb in the other one, I need the force to be L2 in time and I need to lose a derivative. So I mean, I need to put a derivative on u, so h minus 1 in x. Okay. Okay. There would be an intermediate notion of solution, which reinforces a bit Leray solutions a priori. We don't know, actually. I mean, if it's really more restrictive, but the other notion of solution is that you could require also the local energy inequality. So you could require distributionally this property with a less or equal. And this was done by Caffarelli con Nirenberg, because the partial regularity that I will state now is, let me state it with f equals 0. So now I want to, because now, I mean, the program, like, I don't know, the Georgi program on elliptic equation is you build a solution as weak as possible, which typically it's easier to do, and then you try to upgrade the regularity. This works for elliptic equation. It's not clear if it works here, but let's state when f equals to 0, then let's see. Then we have an estimate on the potential singular set. So the singular set of times, now I define it properly, but you can imagine what it is, no? Is compact and has 1/2 Hausdorff dimension equal to 0. So it's of dimension 1/2 at most. And in fact, also the full singular set in space-time has h1 measure 0. So let me draw a picture of what's happening here. So now I define what is the singular set in times, etc. But so let me draw a picture first. Let's take an initial datum. So this is time, and this is x in R3. Let's take an initial datum u0, which we will see it's subcritical. So let's say it's in H1. Okay, it has a bit of regularity. Then you have seen with Elena that for some time you have a smooth solution. And then after some time you lose control. But what in principle could happen is that, so up to here there is a smooth solution. Then as you approach the singular time, what could happen is that there is, say, a point or maybe a collection of points where locally the u loses bounds. So here, u is not L infinity in any small box which approaches these points. This is what is called a singular time. Okay, the singular times are times for which somewhere the solution is not smooth. So this is the set of times such that there exists an x such that u is not locally bounded in any box, let's say, in any cube around yes, for any r greater than 0.
So u is a Leray solution?
U is a Leray solution, so it exists also past. And now, okay, so, and then what this theorem is saying is, okay, these points cannot be, say, a line. No, you cannot, for instance, at this singular time, you cannot have a segment of points where the thing is blowing up, because, I mean, it would contradict the estimates on the singular set. But so this one cannot happen. But what you can see is a set of, for instance, a set of dimension strictly less
It's for
than
the first singular time or for
no, for all, yes. Here yes, exactly. So it says something already at the first singular time, this estimate, but it's also after. Okay, what is the H1 half dimension? So let me write. Recall. Okay, what is the H1 measure of a set? I see typically it's on spirals. Let's say, what is the H1 dimension of a set? Well, I want to cover the set with small balls. And the length of the set, if I make the small, let's say I take a C1 part, if I make the balls small enough, the length of the set is comparable with the diameter of the balls. Okay? So to define the, let's say, H1 measure of a set of E, so let E in Rn. What is the H1 measure of E? Okay, first of all, I have to take the limit, I have to fix a parameter delta, which denotes the size of the ball, and take the limit of this approximate Hausdorff measure. And then how do I define this? The H1 delta of E. As I said, I take the set, I cover it with balls of radius less than delta, and I sum the radiuses, and then I can do it in many ways, and I take the minimum possible over all coverings of, as I was saying, the sum of Ri such that E is contained in the union of B xi Ri. Okay, and I have to consider, and Ri is less than delta, and I have to consider this condition, because otherwise I could have an infinite spiral with infinite length that I cover only with one ball of radius 1, and then I would, I mean, if I didn't suppose that the radii are small, I would be led to think that this curve has finite length, and instead it's infinite. Okay, so this is the H1 measure as I will use it. What time is it? Okay. So then maybe I'll, okay, let's say this proof requires machinery, but this one is very nice and short, and I like it a lot, so I'll present it briefly. So now we discuss how to get the first historical partial regularity bound for Navier-Stokes. And this bound in this class is optimal. I mean, for now, we don't know that H1 of the singular set is 0. Because this bound, one can see, we will see later, we discuss scaling, and it's somehow compatible, optimal for the scaling of the equation. So how does one prove this? So the way I like is the following.
H1 half is defined the same way as...
Yes, thanks. You're right. How do I define H1 half? So do I define the HS measure of a set? Well, with the same definition with S here. And when I define the HS norm, so the idea is now here, if I have a curve, I summing the length. If I wanted a two-dimensional Hausdorff measure, I would sum the areas, the volumes, the areas, sorry, of these balls. If I want the S, I will put an S. Okay, so how to prove this result? So the proof I like starts from something apparently different, which is a version of the local existence result, which now you will tell me if it's the one you have already seen or not. But I mean, the important thing for me is that it works for, let's say, H1 initial data, H1, and the existence time. So if you take an H1 initial data, divergence free, there exists a smooth solution, smooth, in particular, so Leray, but also smooth solution of Navier-Stokes until a time that is explicit, and it's C over the L2 norm to the power 4. Okay. Have you seen this local existence result? No, not yet. Okay, so then we do it. So, and what is particularly important for me is that here the existence time doesn't depend on the C3 norm or the H3 norm or whatever of the initial datum, but really on the gradient of U in L2. And the reason is that I will want to couple that existence information with this quantity, which has the L2 norm of the gradient and nothing else, nothing more. Okay. And C, it's a dimensional, yeah, it's a number, let's say. Okay, it's independent on U0 in particular. So let me prove it. Okay, when you want to get local existence, the difficulty is not to set up a suitable approximation scheme, whatever. It's to have bounds. So a solution exists until there are bounds on it. So this formula is given in terms of the gradient of U0. So in order to get this kind of result, I want to study the equation for the gradient of the solution. So let's differentiate Navier-Stokes. So maybe let's write. We look for an a priori estimate for gradient of U in L2, okay, along the evolution. If I get it, then there will be a way to set up an approximation scheme that actually proves this result. How do I do it? So I want to look at this quantity. Let's differentiate Navier-Stokes. Navier-Stokes, differentiate with respect to a direction E. You can think to a coordinate direction. So I take Navier-Stokes. Well, let me write Navier-Stokes. Then I have, I write it in coordinates. So U dot grad is Uj dj Ui, because when you need to differentiate, otherwise there are too many, I mean, then you don't know anymore on what you're applying what. So then I have dip, and then I have Laplacian of Ui, and then I do it with 4 zeros. So 0. Now I differentiate in a direction E. So here there is a nonlinearity, so I put the derivative outside. The pressure gets a derivative in E, and this term gets a derivative in E. And now I do the only thing we have done until now, energy estimates. So I multiply the equation by dEu I scalar, so no, I multiply the equation by this, okay, and I get dt, and then I get dEui squared from this term. When I here multiply by this is the derivative of the square. I missed. Where? DIE, sorry, here there is also an I, which maybe got covered. Then I get, so I multiply and integrate in space. In space, yes. So this term goes like that. For this term, okay. let's write a bit more explicitly who this is. This is uj, and the dE goes here, dEj ui plus dE ui dj ui. Okay. Yes, maybe let's do something. Let's look first at this term, the Laplacian of dE ui. The Laplacian is a divergence of a gradient. I put the divergence on the dE ui for which I multiply, and I get gradient of dE ui, which, since I integrate by part once, has a positive sign. So it helps me. This is compatible with what we saw already at the energy level. I mean, the Laplacian helps. OK, so this term. Then I have, let's say, the pressure. And the pressure is fine because when I multiply, I have to do the integral of dE I pressure, dEu. Now I integrate ui, sorry. I integrate by parts this one, and I use the divergence-free condition. Fine. So this is equal to 0. And now I have the nonlinearity. The nonlinearity has two parts. There is one part in which I do dEui, dJui, and I extra multiply by dEui. So this, whatever it is, will be bounded by du to the power 3. There are three terms which are gradient, 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 and the extra gradient for which I multiply. And this other term, which would have an extra derivative, so we have to be careful, there is a transport structure, and the integral is 0. So the other comment is that the integral of uj, dej ui, dEui, here you recognize that this is dj of dEui squared. And now again, divergence free implies, so now these I integrate by part, I get the divergence of u times whatever is left, no? And the divergence of u is equal to 0. So this term is 0. So I end up with this nice relation, which now I vary E, the direction E on the coordinate system, and I sum, and rewrite as I control the full gradient of the solution, plus actually a second derivative of u in L2. So these are integrals on R3. In terms of the gradient to the power 3. And here the structure is what we expect. I mean, there is a nonlinearity which is quadratic. When I go to cubic structure, I will see a power 3 somewhere, no? OK. And now, what to do? OK, now I want to estimate this gradient of u in L3. I want to estimate it in terms of the two quantities that I have in the left-hand side. How do I do? Well, I interpolate. This is gradient of u in L2. And then I would like to put, I mean, here you do as you prefer, but my preference is to go first to an interpolation in LP spaces. And here I will have a factor 1/3, 2/3, if I'm not wrong. No, it's the no, sorry, it's 1/2, 1/2. This is interpolation. And then the gradient of u in L6 to the 1/2 is controlled by Sobolev embedding by the double, so the second derivative of u in L2. This is Sobolev. And this is interpolation. Fine. OK. And now, so now actually here there was a power 3. So let me re-establish the power. So this was equal to the previous one, but with a power 3. So there is a 3/2, 3/2, 3/2. And now the point is, okay, this to the power 3/2, I want to reabsorb in this term. The rest will remain as it is. To reabsorb this one, I need to apply, so now I have these two numbers. I want this to the power 4/3 to end up exactly with this quantity. So now I apply Young with exponents 4/3 and 4. Okay? In this way, this term, and Young, I can put an arbitrarily small constant, let's say 1/4, in front of this second derivative, and then I get it square. And then I will have plus a constant, which depends on 1/4. That multiplies the gradient of U in L2. And here there was 3/2, but I need to take a power 4, so 6. Okay? So maybe let me finish this proof here. No, it's not enough. Let's go. I mean, for this one it's enough, but then I need to do another thing. So overall, we have proven that if we call, I don't know, E of t, the quantity du in L2 squared at time t, dt E of t is, okay, here there is a part. This 1/4 gets reabsorbed in the left-hand side, and then I forget it. It's positive, I forget it. And then I'm left with a gradient of U to the power 6, which is E of t to the power 3. This ODE blows up, and this we expected, otherwise we get global smoothness, but it takes time to blow up. In particular, E of t is equal so what do I get? That E of t squared is less or equal than a quantity that has finite time blow up of this form. No? If you solve the ODE from initial datum E of 0, you get this. And you get it for every t until the formula makes sense. So for every t of the form E of 0 squared, no, what is it? I need the t less than this, so t less than 1 over E of 0 squared, C, capital C. Okay, and this is exactly the quantity in the statement. The L2 norm to the power 4. Okay. Now, how do we get a bound on the Hausdorff dimension from such equals 0? Okay. Let's interpret what we have written in terms, so let's interpret this statement in terms, I mean, seen from a singular point. If I sit in a singular point and I look at times right before me, that formula says, okay, the gradient when I approach a singular point cannot remain bounded, for instance. But even more, I mean, it has to blow up in a way in which the point that sits right before me doesn't see an existent time that overcomes me. So let's write it in formula. So for every t in the singular set, and now I take S before t. So the quantity that appears in that statement, which is the L2 norm squared, du at S in L2 squared, cannot be too small. And in particular, it has to be bigger than the constant that appears in that statement, or a friend of it, t minus s to the power 1/2. Okay? Because if this quantity was too small, then I would have an existence time that's starting from this point s that overcomes my point t. And then t would not be in the singular set. Okay. So this, for every s less than t, I have to have this property. In particular, yes. Because here I'm taking the L2 norm squared, there is the L2 norm to the power 4, so I need to take a square root on both sides, let's say. And that t is t minus s. Yes, it's important. I mean, this numerology is fundamental. Because now I have this property for every s less than t. I integrate it for every t here. I can integrate this relation and between t minus r and t plus r, the integral of du squared of s in ds, dx ds, and get that thanks to this inequality, I'm integrating the square root, the 1 over the square root, the primitive is the square root. So I get this for a new constant, maybe there are some numbers to put in, r to the 1/2. Okay. And the way to interpret this formula is to say, okay, so this quantity, we know it's globally bounded because it's in the energy inequality. So we have a global bound on this. Okay, what this formula is telling me is if I sit at a singular point, around me, I need to see some energy dissipated. I mean, and the amount, okay, the amount is not a number. This would be a lot of information. But it scales with a power of r less than 1. And this is a non-empty information. How do we capitalize this information? So now I want to bound the h1/2 measure of the set. So I need to start considering coverings. So given delta, I consider the family of intervals of length less than delta, covering, centered at points at any point in the singular set. And from that, I extract a Vitali subcovering. Vitali. Okay. So now, what is a subco? So now, what I'm left with is so namely, this is a family of intervals ti minus ri, ti plus ri, countable, such that these intervals are disjoint. But if I enlarge them by a factor 5, they cover. So ti minus 5 ri, ti plus 5 ri, cover. Okay. And now, exactly, the covering is made of intervals. Ri is, I mean, half of the length of these intervals that I'm computing. Yes.
the lower bound for the big du or
Yes.
this is true for any s that's before
Yes, then I do it symmetric just because I like symmetric covering. So you can, yeah. I mean, to get this a lower bound, ignore whatever is after.
Yeah.
I mean, you can make it a bit more precise without this, but I like centered intervals. Okay, so we have this covering, and now we compute the H1 half delta measure of the set sig TU. So this is an inf over all possible coverings. Okay, that's the covering I want to use. And so I have, so the H1 half measure is the inf of what? It's the inf of the sum of Ri to the power 1 half. Okay. No, because, sorry, the covering is with a 5, so here I have a 5 Ri to the power 1 half, because I'm taking this particular covering. Okay? So in any case, this 5 is a number. I put it outside, 5 to the 1 half. It's a constant that I will forget in the next inequality. And let's write like that. So sum over I to the power 1 half is here. I use this information to put back. No. OK. So now I have sum of 5 of Ri to the power 1 half. Exactly. Now I use this information with Ri. Okay, so this becomes 5 to the 1 half, the sum of the integral Ti minus Ri, Ti plus Ri, then I integrate in R3, du squared. But now I use the second property of my covering, that are these intervals are disjoint, so this is a number. So this was a constant that I forgot. And this one is bounded by, if you want, the initial datum, U0 squared. So it's a finite number. In this way, we have proven that the H1 half measure of the singular set is a number. H1 half measure of the singular set is bounded by a number. And now, in reality, there I stated 0. But it's easy to see that, I mean, here I threw away a bit. No? I mean, here I'm taking some of, there are these joint intervals somewhere that cover my set. So in reality, this number you can make small, let's say. Maybe I don't do it rigorously, but I do rigorously until saying the H1 half measure is finite. But there is an extra argument that says, OK, this is an integral. I mean, this quantity is then an integral in space-time, and I'm integrating on few intervals. So the quantity is actually small. OK. Proof concluded. Then maybe just a comment. In that statement, I also said the singular set is compact.
Sorry.
Yes.
So it's go to 0.
Yeah. I mean, there is an argument to do. Here, the reality is I'm bounding this by the integral from 0 to plus infinity of du squared. OK? But in reality, when I consider these intervals, so I have to use the absolute continuity of the integral, if you want. When I consider these intervals, the sum of the lengths of these intervals, so here I'm summing sum of the lengths to the 1 half. The sum of the lengths is going to 0. So by absolute continuity of the integral, in fact, this quantity, I mean, in this inequality, I'm losing a lot. In reality, here, you could use the absolute continuity of this integral to have a little over 1. I can give more details. Yes?
What is the difference between a singular set without the t?
Oh, yes, sorry. The singular set without the t. So this is a singular set of times. This is a singular set of points in space-time. That's more difficult to prove. I mean, more difficult. This estimate is due to Caffarelli con Nirenberg in the 80s, so 50 years later than Leray. Okay. Then there I stated the singular set is compact. Okay, it's clear by definition that the singular set is closed. If you want, because the complement are the points around which the solution is smooth or bounded, and is an open set. Then to say it's compact, okay, it's clear that it cannot accumulate, let's say, from an initial datum in L. Okay, this, maybe I don't, okay, the point is, if I take the initial datum a bit smoother, like H1, around t equals 0, there are no singular points, because we have local existence, local smooth existence. Why the singular set cannot go all the way to plus infinity? Well, it's an argument that if you want, given this proof, you can do as an exercise. And the basic idea is, since this quantity is under control, up to taking a very large t, so let me say proof of seeing TU compact. But I give only the idea. So there exists a T star such that the integral from T star to plus infinity of the integral of du squared is as small as I want, epsilon. Okay? So at a certain point, there is no energy left to dissipate, almost no. Okay. And now the idea is, okay, so now in any interval of, after this T star, now we work after this T star, in any interval of length 1, there will be a point of very small energy, I mean H1 norm arbitrarily small as I want. But then if I tune this constant epsilon as needed, the existence time will be like 2. So in any interval of size 1, I have a point of very small energy from which there exists a solution smooth for until 2. Okay, this covers all the line. Then there is no space left for singular points. Okay, I just end wave it for time reasons, but if you want details, I can give you in a break or so. Okay. Then let's discuss the next topic is scaling and self-similar solutions. Self-similar solutions. Okay, you have seen with Elena that when you have your favorite nonlinear PDE, it's natural to look what are the natural scalings. Which amounts in considering a parameter lambda greater than 0, trying to rescale your solution. And typically what you would do is take lambda to a power, alpha for alpha left free, x lambda to another power, and t lambda to another power. And then wonder, OK, for which numbers that I put here is this still a solution of Navier-Stokes? OK, for Navier-Stokes, an analysis 1 computation says that the powers are 1, 1, 2. OK, so if U is a solution of Navier-Stokes, this other guy is also a solution of Navier-Stokes for free. OK. Once you have a scaling, an important thing to look is what are the scaling invariant spaces. These play an important role. OK, when you consider this scaling in R3, you see like that if you compute, now imagine I freeze time. If you compute the L3 norm, or let's say, yeah, I freeze time. I consider the L3 norm in space. When I consider the L3 norm, I have a lambda to the 3 coming from the scaling, from the change of variable in x. and a lambda to the 3 in front, because I'm looking at the L3 norm. They cancel. So this is a scaling invariant quantity. A larger one is L3 infinity, the Lorentz space in X. This, by definition, is the soup of lambda. How is it? U, the measure of the set U less to the lambda to the 1/3. Yeah, here, sorry, I used the lambda for two different things. This is to define the norm. This scales in the same way as L3. On the very smooth side, we have quantities like, if you want to put derivatives, H1 half is scaling invariant for Navier-Stokes 3D. And on the very low side, you will have heard of a result in BMO to the -1. This is also scaling invariant. OK, so this is in 3D. If I wanted to look in 2D, here this 3 would become a 2, because the change of variable in the variable x would give me a lambda to the 2. And so for Navier-Stokes 2D, the energy, which amounts in an L2 norm of the velocity field, is scaling invariant. Yes?
I think that the order of these embeddings is a little bit mixed.
Yeah, you're right. So maybe that one is true. Then if you have an L3 function, this is L3 infinity. And if you have an L3 infinity function, this is BMO. OK. Then you can look at spaces in space-time. And if you've seen the Prodi-Sen condition, I mean, spaces that one typically looks are Ls in T, Lq in X. And this condition is 3 over Q plus 2 over S equal to 1. These ones are the scaling critical spaces. And then scaling critical determines, let's say, everything which is smoother, let's say, is subcritical. Everything that is less regular is supercritical. OK, so for Navier-Stokes 3D, the energy L2 is supercritical. OK. Another thing that one can do once one understands scaling is to consider self-similar solutions. Self-similar solutions are, by definition, so U is a self-similar solution. If it is invariant on the scaling. Which means that U lambda is identically equal to U for every lambda greater than 0. OK. And now we split in, so let me talk of forward self-similar solution. Good question. I think it's lambda to the 3, but I mean, check it on the equation directly. Don't trust me too much. I always go look at it. OK. And then, I mean, then the force has his own invariant, scaling invariant spaces. Forward self-similar solutions are a solution U, which is defined on 0 infinity times R3. Self-similar. OK. So we know that U of xt has to be equal to U lambda of xt for any lambda. Okay. And now I choose a very special lambda. It's a lambda that in the formula of u lambda, I mean, it's a lambda depending on t. So I choose lambda equal to 1 over square root of t. And in this formula, this tells me, using the definition of u lambda, that this is 1 over square root of t. Then I have, sorry, u, little u, of x over square root of t, 1. Okay? Self-similar solutions have a structure. They can be expressed for every time from their representation at time 1. I'll call this representation at time 1 capital U. So U is forward self-similar. If and only if, it can be represented as 1 over square root of t, capital U of the variable x over square root of t. Okay? And this x over square root of t, sometimes I will call this variable psi. Okay? Now, the peculiarity is that this capital U well, if little u is a solution of Navier-Stokes, the capital U will solve a PDE. And the PDE, I mean, this is a function, this capital U lives in R3, from R3 to R3. There is no time in it. The capital U has no time in it anymore. What is the equation solved by capital U? It's minus 1/2 1 plus xi dot grad capital U. So this is the extra term, now I justify it. U dot grad capital U, a gradient of pressure, minus a Laplacian of U equal to 0 or equal to a force. Okay. Why is this the case? Well, because, I mean, when I define U through this formula, I've done something weird in time. In space, I'm doing just a rescaling with a factor, which is square root of t. So the part of the equation that depends on space derivatives is basically unchanged, up to a factor square root of t somewhere that got cancelled. The derivative in time messes up things, no? When I consider dtu and u has this expression, so dt of 1 over square root of t, capital U of 1 over square root of t, what do I see? Well, I see 1 over 2t to the 3/2 coming when I differentiate this, and then capital U. And then when I differentiate here, I get the 1 over square root of t outside. Then I get a gradient of capital U. And then I get to differentiate what is inside. So I get an x over, when I differentiate 1 over square root of t, I get, yes, a t to the 3/2. Okay? And this, now I want to read this equation in the variable psi, no? So you see that here, this is 1 over 2t to the 3/2, which is outside everything. Then I have u of psi plus an x over square root of t is a psi, gradient of u. Okay? This is exactly the term that you see here, okay? Up to cancelling a factor t to the 3/2 from all the terms in the equation. So this is why we see this formula, you can do the full computation. Okay. So now, how does a self-similar solution look like? So the idea is you have this profile, capital U, that you have to think as a smooth profile. Capital U, which is equal to U at time 1. And then, let's say, as you approach time equal to 0, which is what I'm interested in whenever I will do non-uniqueness or so, this profile gets rescaled by a factor square root of t, so it gets more peaked. So this is U at time, let's say, a bit less than 1. No? It gets, and it goes up. Okay. At time 0, what can you see when you look at a self-similar solution? So initial datum. Well, it has to be an initial datum that is invariant for the scaling. So invariant for the scaling means there is no time is equal to 0. Lambda u of has to be equal to lambda u0 of lambda x. This means the initial datum is 1 homogeneous, minus 1 homogeneous. Okay. Yes, so all initial data for self-similar solution are minus 1 homogeneous. And if you look only at the profile, capital U, how do you read the initial data? Well, you read it at plus infinity. The U0 equal to U at time 0. Red on the self-similar profile U bar means that when you take U of psi, it approaches U0. So minus 1 homogeneous means that you can represent it as a 1 over modulus of x, U0 bar of x over modulus of x. And this means that this approaches this. Psi goes to 0 as psi goes to plus infinity. So on self-similar profiles, the initial datum is red as an asymptotic behavior. Yes? Capital T and capital F, yes, exactly. So you need to talk of self-similar solution, you need a force that is invariant under scaling. And this capital F corresponds at the profile at time 1 of that force. Thanks. OK. Last consideration about self-similar solutions is that we have introduced self-similar solutions. We have seen that there is a change of variable that plays an important role on them. It will be important for the next classes to look at this same change of variable more in general. So you can introduce self-similar variables. That is, you consider psi equal x over square root of t. Now, this seemed a change of variable that played an important role when reading the self-similar profile. So this I can do for any solution, okay? And then for time, there is a reason to, I mean, in principle, you could consider the variable psi t. In reality, often you call tau the logarithm of t. because it desingularizes the equation of a factor t, the time derivative, when you read it in terms of the log as a 1 over t. And that's useful. So however, to keep in mind, this variable is in R3. If t, so we are interested typically in t in, let's say, in 0 infinity. But we are interested really in time 0 as an important point where non-uniqueness can happen. Time 0 becomes tau minus infinity. Okay? So in self-similar variables, the non-uniqueness will stem from minus infinity. Okay, this to keep in mind, otherwise one gets lost easily. And then u of xt, you can represent it in general as 1 over square root of t, capital U of psi tau in this. So any function of x and t you can represent in the variables psi and tau through a formula like that. And this solves Navier-Stokes. If and only if the profile capital U solves another equation, which has to do, I mean, it's basically Navier-Stokes with the extra factor that we found up there for the time derivative that is a bit funny. So d tau capital U plus, no, minus 1/2, 1 plus psi dot grad capital U. This is the extra factor that comes from the time derivative when you use this funny expression. And then I have the standard parts, capital U dot grad capital U, the gradient of the pressure, the Laplacian, and the force. So this is what
It's not the same U as before. It's a function of tau.
exactly. Now the difference is, so the analogy with the capital U that there was, what was before was a stationary solution of this, no time derivative. Now what I'm saying is I can do it more in general. I can re-include time and just rewrite the equation in terms of this. This will play a very major role in the next lecture, but yeah, the important take-home message is you can rewrite Navier-Stokes in this other system of variables in space-time. And Navier-Stokes modifies accordingly. Okay. The next thing I'd like to do is to consider also, one can look at backward self-similar solutions. That are just self-similar solutions in is you consider now a self-similar solution which is defined on negative times. So a backward self-similar solution is a solution defined on negative times and self-similar. Okay. In this case, I can redo the trick to say, okay, it's generated by a profile, but I have to do that trick with the square root of minus t as a game player. Okay. So let me redo it. U of xt is equal to u lambda of xt. This is for any lambda. I choose lambda equal square root of minus t. And I get that this is equal to 1 over square root of minus t, u of x over square root of minus t. What happens when you consider a backward self-similar solution? The picture there, where you have a certain profile at time 1 that gets rescaled, is now you have reversed time. So it's a profile at time -1, which is smooth, decaying, which gets rescaled as you approach time t equals 0. So as you go forward in time, and gets peaked as you go forward in time. This is a possible blow-up scenario, no, for a PD. And I mean, the self-similar structure is really what everybody looks at to find blow-ups of PDs. So you have this is a little u. So u backward self-similar as before is if and only if you can represent it as 1 over square root of t, a capital U of the self-similar variable with a minus everywhere. And now the observation is that if u is different from 0, is smooth, and solves the backward self-similar equation that, as you can imagine here, I've changed t to minus t. When I look at the equation, the backward self-similar equation is the same, exact same as this one, just with a sign change. And the sign that changes is this one. This becomes a plus. So this I call Navier-Stokes in self-similar. And Navier-Stokes in self-similar, this is a blow-up. This is a finite time blow-up. So can one find blow-up of Navier-Stokes?
I understand in this case, your profile do not depend on tau.
Correct, yes, solved. Now it's stationary. Which, if you want, is what I wrote up somewhere, no? Is what I wrote there. So it's that equation, but again, with the plus instead of the minus, because I'm looking at backward self-similar. Then I would have found a blow-up theorem. This blow-up is not there, actually. Nekas. Sverak. Acta 96. The theorem is Navier-Stokes has no self-similar blow-up. So in particular, if U in L3 intersected H1 lock solves the backward so Navier-Stokes backward self-similar, let me call it. As I said, the backward self-similar version is with a plus, and in this equation, there is no dependence on tau. So this is backward self-similar, and the original one I would call Navier-Stokes in self-similar. Then U equals, then it's 0. And also, I mean, this with no force. The force would immediately make blow up things. Solves this. Okay. So if you have no force and you are a backward self-similar solution, then you are not. You are zero. Okay.
Analog of this for the, so this is for the exact self-similar solutions. For non-exact, when you have the tau variable.
No, exact. Anything can be expressed as non-exact. If there are asymptotically self-similar solutions, I think this is something that everybody is looking for right now, like with the computational methods. These are the ones that one tries to find. Sorry?
And the forced exact self-similar.
This, by definition, I mean, this you find a lot, no? You take your favorite self-similar profile, you call force what you have there, that's a solution, and it blows up. Okay. Yes?
Explain back why you need to remove this, like, to you to get this finite time blower? Or I don't really get why this stationary thing gives you...
Wait, can you repeat the question?
Why taking a stationary solution of backward Navier-Stokes gives you blower? Maybe I misunderstood.
Okay, so yes, if you take a stationary solution of this equation, when you read back in original variables, you have a solution of this form. When you approach time t equals 0, this solution is unbounded. Let's see. I mean, this solution, if you want, becomes at time equals 0 for the same reason as for forward self-similar solutions, becomes -1 homogeneous. So in particular, it's unbounded around 0. Sorry?
It will not be true if you still have this.
No, in general, not. I mean, any solution of Navier-Stokes can be represented in this system of coordinates. So it's not that everything blows up at 0. OK. So now we have 5 minutes left. It's too little. I want to give you the proof of this theorem. It's not, or at least the substantial part of the proof of this theorem. Without too many technical details. It's not too long, but I do it in the first 15 minutes of this afternoon at this point. And maybe I use the last 5 minutes to tell you a bit the plan of the next 2 lectures, which will go more in detail. So first, proof of this result, which I think is a very important piece of literature, and relies on, let's say, on an exact relation, on an exact maximum principle. A maximum principle is not, so a PDE that has a maximum principle. A maximum principle is not something you expect in fluids, typically. But when there is, it gives a lot. So this, and then the next thing I would like to do is to discuss instead the question, are Leray solutions unique? And I want to give you an overview of several different approaches that have been tried on this problem. So maybe a first thing that I will not discuss instead is a result of Buchmaster and Wickel. Around 2020, which is based on convex integration and gives non-uniqueness of distributional solutions. So just to say, the class in which you look at the uniqueness problem is very important. Distributional solutions are non-unique in a very bad way. And this is via convex integration, which is somehow the technique that was brought to fluid dynamics to approach the on Sager conjecture by Dell'Ellis and Szekelydi. Okay, this I will not discuss. Then, I will discuss instead the program of Jia-Sverak. Okay, let me make a chart. Let me say. So this is Jia-Sverak and then also Guillod. And it's around 2014 and some years after. Okay, there are several papers there. And Jia-Sverak, in a first Invenciones paper, they study in a systematic way forward self-similar solutions. And what we will see this afternoon is that self-similar solutions for small data are, let's say, easily or with classical methods shown to exist. Jia-Sverak prove they exist for any large data with the property that I said, -1 homogeneity, because otherwise it makes no sense to talk of self-similar solution, and 0 force. So Jia-Sverak, Guillod do so just to schematize this, self-similar Navier-Stokes, no force, but and non-uniqueness. But the problem of this is that a part of their proof is just a numerical. So there is numerical evidence of non-uniqueness, but at this point, no proof. And they will enter a lot in the program they try to develop, and also why they can do, I mean, they do a nice numerics, let's say. The very unstable numerics you can do is the one in which you really try to build a blow up, because you have to numerically simulate something which blows up. Instead, they do a numerics on a different problem, not really in building the solution, but in finding unstable eigenvalues of a smooth object. This is better, I mean, because you are dealing with smooth things. But still, it's numerics. Then the other paper I would like to present is a result with Dallas Albritton and Leray-Hopf Brue. And here maybe I just give you the statement. There exists a force, so this is with force. But it's rigorous. Of Navier-Stokes, and says that there exists a force which in reality is a self-similar force, but in particular, to stick to what we have seen until now, it's an L1 in time, L2 in space force, so it works well with the Leray theory, such that Navier-Stokes has two different Leray solutions, starting at u at time 0 equal to 0. So there is no initial datum, but there is a force. And these two solutions in reality are a self-similar one and something which is very close to a self-similar one, let's say, which is asymptotically self-similar. So it's a smooth perturbation of a self-similar one. Okay? And then to prove this result, we will rely on an analogous question on something that you have seen with Elena, which is the the question of sharpness of the Udovich theorem for 2D Euler. So there are results on so 2D Euler with vorticity omega at time 0 in LP, p less than infinity. So for p equal infinity, you have uniqueness. You can ask whether you have non-uniqueness for p less than infinity. And this is done numerically by Bressan-Chen. There is really an explicit scenario in the last, I don't know, 2019 maybe. There is really an explicit scenario where it's expected there is non-uniqueness. And rigorously by Vishik. By Vishik in 2018, I don't know exactly, 2018, maybe a bit later. Sorry, 19 as well, okay. In 2 papers, so these are 2 papers that we have revised in a reading group with, started by Camillo, and that, I mean, we started when I was visiting IAS, and it's, so we revised this in, say, lecture notes with some people Albritton and Brue, and then I not say the others because I would forget somebody. So we are like 7 authors. And Vishik does a rigorous proof, but with a force. With a force. So on both problems, somehow, the problem with no force, but a non-trivial initial datum at that point, is open and resists several attacks, whereas numerically it seems to be the case. Okay. Yes, are there questions?
Why is the force trivial in the blow-up case, but not trivial in the non-uniqueness?
Yes, because let's see. Well, I mean, yeah, I don't have a nice answer to this. Let's say, to the blow up is trivial because you fix a profile, it blows up. Well, it's still true, and we will use it, that if you fix a profile and you look for a forward similar solution, you find it with a force, but it's not clear. I mean, many of them will have only one solution, let's say. I mean, I can prove that many of them, there is one solution. Like small data, small force ones, the solution is unique. So it's not real that you actually generate it in this way.